This is part 2 of chapter 2, and we're going to pick up on slide 14. In segment 1, we introduced various definitions, and we're going to start seeing how those play out in data analysis. And a fundamental task is estimating a trend by least squares. We're going to analyze a time series of global mean annual temperature downloaded from climate.nasa.gov. These data are degrees Celsius measured, a global temperature measure measured as an anomaly from a 1951 to 1980 base. What does it mean to be anomaly? This is climatology jargon for saying that they took the average over the interval 1951 to 1980 and subtracted that from all the other time points, so it sets a baseline 0 for that average. Okay, here's the data, just to look at the structure of the global temperature variable. There are 3 variables: year, annual anomaly, moving 5-year average, which we're not going to look at so much. One of the first things you do after you've just looked at the variables is you plot them. And here we go. This is the global warming story that we know all too well. So there's a trend going on up here, and basically ever since around 1980, there's been a fairly unambiguous global warming signal. Before about 1980, it was all, it was a bit more subtle to believe in the greenhouse. In particular, if you just look in this time interval here between 1940 and about 1975, you could have been forgiven for thinking that maybe we had a global cooling problem. Anyway, now we're focused on global warming. These data should make all of us pause for thought about the future of our planet. And perhaps the question in this course is, what can statisticians do? What's the role of time series analysis? And here's one perspective on that. So understanding climate change involves understanding the complex systems of physical, chemical, biological processes driving climate. That's what geophysicists, climatologists spend their life studying. Some of them build gigantic or very complex models to capture all important parts of the global climate processes and try to produce a description of what's happening that's good enough to explain the past and predict the future. But there's also value in relatively simple statistical analysis, which is really more focused on the core data. You want to understand temperature, you measure temperature and you see where it's going. And you can see how different things are or are not changing, or are not correlated. Here's a quote from Science a few years ago, back in 2015, that I've added some emphasis. Scientists are still debating whether, and if so, how warming in the Arctic and dwindling sea ice influences extreme weather events at mid-latitudes, the kinds of things we see in North America. Model limitations, scarce data on the warming Arctic, and the inherent variability of the systems make answers elusive. These are all things that statisticians know about, think about, and study. Okay, so if you just look at the data, perhaps the simplest model that makes some sense is a quadratic model for the trend, where mu of t is beta 0 plus beta 1 t plus beta 2 t squared. And we want to set this up as a classical linear model, we use matrix notation. We set mu to be mu1 through mu(n) as a column vector, and we set beta to be a vector of parameters. We set z, the vector of covariates, to have 3 columns, a constant, the year, and the year squared, and then we write mu equals z beta. This is the matrix approach to linear regression, which I'm expecting most of you have seen before. I have a reference coming up if you want to check it out. One difference in time series, we tend to reserve capital X for a random variable for a time series model, and so we use Z for the matrix of covariates. Now, we can write Y as a column vector. I guess I either have to have stars or not have stars. So I'm going to cross out that star, and just this is a general possible data set, not the particular data set, because I'm going to use this Y to define the ordinary least squares estimator of beta hat OLS for any set of numbers Y is Z transpose Z inverse Z transpose Y. And then if you evaluate that at the data Y star, you get the ordinary least squares estimate, beta hat OLS. And that's the computation carried out in R by the widely used LM function. So LM fit here is our fitted linear model object. And if we want to fit that, we can do it as LM annual twiddles, or depends on, year plus I year squared. The constant term is there automatically in LM, and we need this I thing to tell R that year squared is a function of a variable that we want in the model. Here's the summary of the fitted LM object. When we're estimating trend, we're most directly interested in these things here. These give the estimated trend fitted by least squares. Now there's various other statistics, standard errors, hypothesis tests, p-values, t-values, and so on here, which we haven't got to yet, but we certainly have a least squares trend. We'll think what the other things mean in due course. When we have a fitted trend, perhaps the first natural thing to do is to see if it looks appropriate given the data. So you see how visually it fits the data. And here I've given you a plot and just some code to construct the plot. And it seems like it's doing a reasonably good job. So let's say the overall estimated trend seems a reasonable fit for the data. As statisticians, we want to attach uncertainty to parameter estimates, possibly, and uncertainty to a forecast, certainly. And to attach uncertainty to an estimate, you need a model. To do least squares, you don't really need a model. It's a defined thing to fit something by least squares without having a model. But anyway, let's think, what is the standard regression model for this Y1 through N? Well, the usual model behind ordinary least squares is the independent error model, which has a special name in time series. It's called the white noise error model, Y equals Z beta plus epsilon, where epsilon is independent, identically distributed random variables, mean zero, constant variance. So expected epsilon n is 0, var epsilon n is sigma squared, and all the statistical inference on the summary from the linear model in R is based on this modeling assumption. Now, under this standard OLS white noise model, the estimate beta hat is unbiased. And let's just go through some algebra to check that. If you want to, what does it mean to be unbiased? It means that its expected value under the model is the true parameter value. So let's calculate that. The expected value of beta hat OLS evaluated at the random variable y is, by definition, the expected value of z transpose z inverse z transpose y, and y is z beta plus epsilon. That's how we get to the second line here. And then we use the linearity of expectation to take the z transpose z inverse z transpose outside the expectation, and then the other z beta outside because it's just an additive constant. And then the expected value of epsilon is 0 because that's how our model was constructed. So we get z transpose z inverse z transpose z beta, and then z transpose z inverse times z transpose z is the identity. The identity times beta is beta, so that gives us unbiased. Another kind of famous result for linear models is that the ordinary least square estimate beta hat is the minimum variance unbiased estimator for model L1. Under this model, we can also calculate the variance covariance matrix of beta hat under the model. And this is, if you want a reference for linear models, a good kind of practical one that also has enough theory for this course is Faraway 2002. The references are at the end of this of the slides. So the covariance matrix of beta hat OLS is sigma squared z transpose z inverse. Z transpose z, we know these are the covariates, they're in the data set. Sigma squared is a parameter, we don't know it, so in practice we estimate it, and the ordinary least squares estimate is a sample variance square rooted, and here we do, for OLS we divide through by 1 over n minus d. We don't do the kind of 1 over n thing that happens in the autocovariance estimator. D is here as the number of covariates, which is the number of columns of Z. Okay, so that's a review of ordinary least square estimation. Oftentimes in time series, we want to consider the possibility that the errors are correlated, and we have to work out either what to do in that situation, or if we persist with doing ordinary least squares, what does it mean to do ordinary least squares when the errors are correlated? That's going to be part 3.